In this video, we're going to have a look at one-dimensional kinematics problems for a Physics 1 class. Many of you who take physics, this is the first time you encounter many physics equations that you must solve. And I'm here to help you solve those today by example. That's on this edition of High Peak Education. What is going on, everyone? Hope you're having just a wonderful day, and thank you for watching the channel. So, we have many kinematics problems coming at you. These kinematics problems are going to be one-dimensional motion, typically along an x-axis, constant acceleration problems, and we use the kinematics equations. And because of the kinematics equations, it turns out there's going to be 5 kinematics variables, namely the initial and the final velocity, the displacement, the time, and the acceleration. We assume the acceleration is constant, and from that we can derive several equations, namely 5 different equations that tell us how to describe the motion. And I'm going to show you a process that is a recipe or an algorithm about how to know which equation to choose each time, guaranteed, no matter what. That's coming up right now.
Problem. It says a car is 2.0 kilometers west of a traffic light at t equals 0 and 5.0 kilometers east of a traffic light at 6 minutes. Okay? It says assume the origin of the coordinate is the light and the positive x direction is eastward. What are the car's position vectors at those two times? B, what is the car's displacement between 0 and 6 meters? Okay, so let's start to work this out. So let's draw first a motion diagram, shall we? The car is 2.0 kilometers west of a traffic light at t equals 0 seconds. Now let's assume the traffic light is the origin. So right here is the traffic light. And again, this is x equal to 0 because we're told that in the problem. That's the origin of the coordinate system, right? But the car starts off 2 kilometers west of the traffic light. So let's call this time equal to 0 seconds. And we know that this is x equals negative 2.0 kilometers. Now notice, they give us 2.0 kilometers there, but it says west. Now typically east is in the positive x direction, and then west is in the negative x direction, okay? And then the car ends up 5 kilometers east of the light at 6 minutes. So if this is 2 kilometers, let's say 5 kilometers is, I'm just estimating, but probably somewhere over here, okay? So let's let this be x, make that a little better, 5.0 kilometers, okay? And you can put a little positive on that just to remind yourself it's to the right of the origin if you like. And we know that this is t equals 6.0 minutes. So by the way, if you want to use the language of what we've already seen in the notes, we could call this x1 and time 1. We could call this x2 and time 2. We want to know the car's position vectors at these two times. And we want to know B, what is the car's displacement between 0 and 6 minutes? Well, let's think about these position vectors. Remember, vector just means magnitude and direction. In fact, let me write that down. So vector means magnitude and direction. Okay? In other words, that means size and orientation. Okay, so this is what we mean by a vector. So magnitude and direction, which is the same thing as size and orientation. So in other words, how far is the magnitude of these displacements, but in which direction, positive or negative, east or west, are we talking about? To start off, the first vector, so that's x1, is going to be just negative 2.0 kilometers. So what you could, kilometers. So what you could also say is you could say 2.0 kilometers west. So west tells you direction, right? Then how about x2? Well, x2 should be positive 5.0 kilometers. Now, by the way, whenever you start using negatives and positives, you should have an axis defined. You can only talk about positive and negative like in terms of direction and all that, if you have already established an axis. Part B, what is the car's displacement between 0 and 6 minutes? Displacement we know to be delta x, and that's going to be x2 minus x1. Now notice x2 is positive 5.0 kilometers, and then x1 is negative 2.0 kilometers. Notice we've got minus a negative, which is a positive. So that's going to be 5 plus 2 kilometers, sorry, 7.0 kilometers, 2 significant digits. Now let's have a think about why this is. It's because the car goes 2 kilometers to the traffic light and then 5 kilometers to its new position. So the total is 7 kilometers. So the positive symbol plus isn't necessary, Joseph asks. No, it is not. It's not, but only because we're learning this sort of for the first time, sort of emphasizing it, but it's not necessary. Do 2 problems here. I want to do a graphical problem, then I'm going to do a more sort of calculus type problem. So let's work on number 33 and then we'll work on 35. So let's start off with problem 33. Now, by the way, in order to do problem 33, it says, given the following velocity versus time graph, sketch the position versus time graph. Now, by the way, what I would also like us to do is also sketch the acceleration versus time graph. So we want to get the position versus time graph and the acceleration versus time graph out of this. So let's label these. Always a good idea to label. So I want this to be the time axis. So this is the positive time direction. And I want vertically upward to be positive velocity and negative velocity down here. For this graph, positive acceleration, negative acceleration. And then let's have this be positive x and then negative x. So let's assume that this particle, remember the particle is like the little dot or something. This particle is just going along an x-axis. So in fact, let's even call this vx and ax. The subscript just indicates which axis it's along. Imagine that this velocity versus time graph here is in green. Because remember, the acceleration, this should be the slope of the velocity graph. And we're thinking about the slope as a function of time, and we're also thinking about the derivative here, because we're thinking about instantaneous slopes. Well, right here, it looks to me like the velocity is no slope. Does everybody see that? So it looks like no slope. So that's like no acceleration. So that's like right here, okay? Up till about this point. Does everybody see where I got the grid on there? Up to about that point. Then it looks like, look at this, it looks like it goes concave down. Do you see that? So what that means is the acceleration's not constant, it's actually changing. And since it's concave down, the acceleration is going to become more and more negative. So up till about this point, so I'm just going to use some of these lines as sort of reference. Up till about this point, I think the acceleration's becoming more negative. Does everybody see how I'm getting that? And then at this point, then the slope is negative, but it's roughly constant. Do you see that? And that happens for a while up until about here. So the acceleration's negative, but it's roughly constant. So let's go like so. Negative but roughly constant. There, okay. So negative but roughly constant. Then when we get to this point, look at this. See how it's rounding up again? It's changing to concave up. So what that means is the acceleration is going to become more positive. Now keep something in mind. This much of acceleration down looks to be about this much acceleration up. So I guess my point is we probably go back up here to about 0 acceleration. And then we flatten out again, so we've got no acceleration for the rest of the time. Let's do the position versus time. Well, the position versus time, I want to do that in a nice color blue. So let's do nice color blue here for the position. Now, keep in mind, the position versus time is going to be the area under the curve. Does everybody hear me? So in other words, the definite integral with respect to time is going to be the position versus time. So the whole idea is we're going to accumulate, so to say, position. So first of all, this is going to be area of the v versus t curve. So it's going to be the area of the v versus t curve, vx. Then we can start off the position wherever we like. Assume the particle starts at the origin. So if the particle starts at the origin, that's because if we have the velocity versus time graph, we don't have information about the particle's original position. So we are free to choose where we want it to be. I think I got a question coming in here. Wait, why does the acceleration become constant again from 3 to 5? Okay, good question. So I'll pause and go back to that. Okay, so couple things. So first of all, the reason I said that the acceleration became more negative here because of concave down, that's basically because this is a non-constant acceleration. And when I say non-constant acceleration, that's technically like a non-zero jerk. So the acceleration's changing with time here, technically. So we don't do that very much in this class, but that's the idea. The acceleration is changing, but it's concave down, it's becoming more negative. But here, when it rounds up, it's going from negative to more positive. But the idea is that as much as it was concave down here, it's concave up there. So that's why I had the acceleration come back to about 0. Now here, I mean, partly you have to forgive my, you have to kind of forgive my crappy, like, doing the green on top of this. It looks to me like there's very close to 0 slope right there. And so from about here to about here, I'm going to say that the acceleration is almost 0 because the slope there is almost 0. So that's why I just had the acceleration at 0 the whole time there. Okay, so back to what I was saying about position. So since we don't know where the particle starts, we are free to choose where it starts. So let's have it start at the origin. So the particle is going to start right there. Everybody see that? Right there. At the origin. That's x equals 0. Neither positive nor negative. Well, I think this is all positive area. Do you all see that? This is positive area. So the positive area is growing at a nice steady rate at first. Why? Because the velocity is roughly constant. So up till about this point, when the velocity is constant, the slope should be nice and linear. I hope you see that. But then the velocity is getting less. And it's getting less, but it's still positive, so it should probably go something like this. Okay? Up till about, say, here. And the object is still moving to the right, but it's, it actually stops moving to the right there. Because I want somebody to tell me in the chat, what is the value of the velocity? What's the numerical value of the velocity right there? Isaac says 0, and he is correct. Nicely done. Notice that right here. Everybody look, right there, right there. The velocity is 0. You see what I'm saying? Because up here is positive velocities, down there is negative velocities. So by definition, listen to me, by definition on the position versus time graph, we better be at 0 slope right there. In other words, we better have a horizontal derivative. Does everybody understand what I'm saying? Okay, I hope so. And then come down here. Notice that now we're getting into negative area. So this right here is all negative area, right? So this is all negative area. And since this is negative area, we're going to start the particle moving to the left. Or sorry, I said that wrong. The negative area looks a little bit larger than the positive area. Slightly. Just slightly larger. So as a result, I think we're going to change the position in the opposite way like we were, because we've got negative slope, or sorry, we've got negative velocity values. So that means we better have negative slope on the position versus time graph. So it should go like this. Now let's come to this point. So this point right here is where we change from negative slope. So here we have constant, so up to here we have constantly changing negative slope. But then But then what we have is we actually have becoming less and less negative. So that's becoming like this. But then we're still moving to the left, but at a roughly constant rate. So it's going to be something like this, all the way till about the end. And notice that we're going to sort of move back past the left, past x equals 0. Because again, at least to my eyeball, this negative area is a little bit larger than this positive area. So this right here is a sketch on the top figure of position versus time. And then on the bottom, acceleration versus time. So that's what we've done. And we can get both of those from the velocity versus time graph. Okay? You may ask, could this black axis, so let me just do a quick and dirty sketch over here. You may ask, could this axis that you see up there with the blue curve be exactly the same if you had said, say, x equals, I don't know, negative 10 meters? Would you have the exact same shape, you know, like so? Or would you have the exact same shape, yeah, like that, and you just started at x equals negative 10 meters? And would it still be correct? And the answer is yes, because this figure and then this figure are exactly equivalent, except for you just set your initial position to be, say, to the left of the traffic light, like the last problem. But I'm setting it that I'm starting right at the traffic light. In other words, right at x equals 0. I mean, that's usually the easiest, but you don't have to do it that way. It says a particle moves along the x-axis according to x of t equals to 10t minus 2t squared in meters. What is the instantaneous velocity at 2 seconds and 3 seconds? That's t equals 2 and 3 seconds. B, what is the instantaneous speed at those times? C, what is the average velocity between 2 and 3 seconds? Let's go ahead and have a look at this. So if we've got the position as a function of time, and we want the instantaneous velocity, somebody should tell me in the chat what we need to do. If we've got a full position versus time function, and we want to figure out what the velocity is at various times, what mathematical operation should we perform? Let me tell me in the chat, please. What mathematical operation should we perform? Isaac says derivative, Ethan says derivative, and I agree. Very nice. Okay, so we are going to take the time derivative of this position function, okay? Now, by the way, some of you have seen it this way for part A. Some of you have seen that v of x is equal to dx dt. That's often what you'll see me write this semester. Again, that's Leibniz's notation. Or you can certainly write this. Watch this. X prime of t, right? Isn't that what you usually do in calculus class, where this prime just means derivative, right? I think this is a little bit more informative. Helps you to know that the position changes with time. But anyway, either way. So if we take the time derivative of this, I think we'll have, what, 10 minus 4t. And that's our function, right? That's our v as a function of t. Okay? And remember, this would be vx. Let's assume it's along the x-axis. Okay, so we want the instantaneous velocity at 2 and 3 seconds. Well, I think we just need to plug in, right? So we just need v of x at t equals 2 seconds. And let's put the numbers in. So that's 10 minus 4 times 2. So that's going to be 10 minus 8, which I think would be 2 meters per second. 3 seconds, right? That's all I need to change. I mean, my old friend Luke used to say, lazy people make the world go round. It's called efficiency. So I'm changing that to 3, right? So I've got 10 minus, and then now I think this is 12. So let me just get rid of this part right here. Okay, so we've got 10 minus 12. And I think that's going to be, let's see, negative 2 meters per second. So those are our velocities. Okay, part B. What is the instantaneous speed at those times? So speed is just going to be exactly The magnitude of the velocity. So another way to think about this is if you want to write this out sort of in symbols, is that s, or yeah, speed, if you want to call it s, but s is equal to the absolute value of Vx, right? That's a more mathematical way to say this. The speed is just the magnitude. Irrelevant if it's positive or negative. So I want to know, what is the instantaneous speed at those times? In this case, I think the speed is equal to 2 meters per second. And then the speed, even at 3 seconds, is 2 meters a second. Okay? Because the idea is that, I mean, think about this. Your car's speedometer is not a velocity-ometer, nor is it a direction-ometer. Everybody know what I'm saying? Like, your car's speedometer is just measuring how fast you're going, irrelevant of direction. So that's why we call it a speedometer. Okay? So, I think we've got that taken care of. Let's look at part C. Part C, what is the average velocity between 2 and 3 seconds? Well, let's write this down. So this is, first of all, it's going to be the secant line slope. And remember, the secant line slope is going to be the change in the vertical axis variable over the change in the horizontal axis variable. So it's going to be x2 minus x1 over t2 minus t1. We called this Vx, we called this Vx, but we can call this Vx1, and this is Vx2, right? But what we really want to know is we want to know the position at time 2 and 1. We know what the times are at time 2 and 1, or 3 seconds and 1 and 2 seconds, respectively. Well, I think we need to plug into the original function those times. So x2 is going to be the original function with time as 3 seconds plugged in. So that's 10 times 3 minus 2 times 3 squared. And then that whole thing minus, and I'll put this in brackets, let's see, 10 times 2 minus 2 times 2 squared divided by, let's see, 3 minus 2. So let's perform this calculation, and let's see if I can use my calculator here. So we've got, let's see, 10 times 3 minus 2 times 3 squared, and all that minus, parenthesis, 10 times 2 minus, oh, nobody squawked at me. There should be a squared on this other one. Maybe it didn't come over in the copy. It should be squared. Apologize for that. 2 times 2 squared. Sorry for that. So 2 times 2 squared. Close off this parenthesis. Now I'm going to close off the numerator and the denominator because I want to divide this all by 1, which is somewhat irrelevant because that's 3 minus 2, which is 1. But looks like somebody else who got this calculation. Somebody let me know in the chat. What did you get when you got this calculation done? Isaac said you got 0. Anybody else confirm that? Grace got 0? Yes, that is 0. So 0 meters per second. And let's see if this is reasonable. Let's go back to board 4. Notice on page 4 here, notice that we had a positive velocity, then a negative velocity. And this to me looked like a parabola. Does everybody see that? So I think we're on one side of the parabola at 2 seconds. We're on the other side of the parabola at 3 seconds. Okay, so I used Desmos, and this is what I got. I'm going to make this just a little smaller. Okay, so hopefully you can see this here. On the vertical axis is meant to be x. On the horizontal axis here is meant to be time. So notice that when we were at 2 seconds, I think we were right there. Does everybody see that? This is 2 seconds. And at 3 seconds, I think we were right here. Hopefully you see that. Here's 3 seconds. So halfway between 2 and 4 is this 3 seconds. And then notice that this is the instantaneous velocity. That was 2 meters a second. And then here's this other instantaneous velocity. This is negative 2 meters a second. But notice the secant line slope, that's, let me change color here to emphasize what I'm talking about. This secant line slope is the average rate of change between these 2 points. But notice the average rate of change between those 2 points is exactly 0. So you can get this either graphically or analytically. I think analytically is definitely faster, but graphically should confirm. Airplane starting from rest moves down the runway at constant acceleration for 18 seconds, then takes off at a speed of 60 meters per second. What is the average acceleration of the plane? Let's write the definition of average acceleration using the equation editor. Okay, there we go. That's what I meant to do. Does everybody see that? Okay. All right, so there it is. Let's write down our knowns. Today, always a good idea to start off by writing down your knowns. Okay, so an airplane starting from rest. So starting from rest, let's get that nailed down. So starting from rest, I think that means Vx1 equals 0 meters per second. Moves down the runway at a constant acceleration. So Ax is equal to a constant. In other words, this is just a single number. Now, why is that important? You may not realize why that's so important, but let me just pause for a second. I'm looking straight in the camera. Look at Zoom if you need to look at me. I'm looking straight in the camera. The reason that's important is because if the acceleration is constant, we can just use algebra. We don't have to use calculus. Does everybody hear what I'm saying? Calculus is for non-constant things, right? When something's, say, changing in time. When the acceleration is constant, we should just be able to do algebra on this problem. Okay, so we don't need to bring in Newton and Leibniz here. So let's see. Constant acceleration, 18 seconds. So by the way, often we set t1 equal to 0 seconds, and then t2 is 18 seconds. So almost always in physics, whenever we're doing a time change, we set the initial time to be 0. In other words, when we start the stopwatch. And then you could just from this just say that the full delta t is just 18 seconds. All right. And then it takes off with a speed of 60 meters per second. And by the way, let's assume that the airplane, since it has a constant acceleration, it's going to have a constant direction. Okay, so let's kind of sketch our x-axis here. So here's our x-axis. And then here's the plane, something like so. Let's give it a tail. It's not a great sketch, but it's not terrible, I guess. It's got some wheels. But anyway, the point I'm trying to make is I don't think it's going to change direction. So I think that even though they gave us the speed, we can say the final velocity, that's x vx2, is 60 meters per second. And it's positive as long as this thing is going to the right. So this is the velocity direction. Okay? All right. So we can break down this average acceleration into the following. We can break this down into vx2 minus vx1 over delta t. Well, wait a second. We know what vx1 is. That's 0. So we can just put a line through that and do 0. And then we have vx2 and we have delta t. So we can just put the numbers in. So I think we've got 60 meters per second over 18 seconds. Okay, so let's calculate that. So we just need 60 over 18. And we'll probably do 2 significant digits. So that's 3.3. It's actually 3.3 repeating. But it's going to be approximately 3.3. And that's going to be meters per second squared. It's acceleration. Furthermore, do you see how the units work out? Meters per second divided by seconds gives you meters per second squared. By the way, sometimes I do S for seconds. Sometimes I do SEC for seconds. S sometimes looks like a 5. So I don't want you to be confused. But when it's clear, like, it's meters per second or it's got a squared on it, you don't necessarily need SEC. But The SI abbreviation is S, but again, I don't know about you, it sometimes looks like a 5, so sometimes I just write out SEC. I don't want you to get confused, it really means the same thing. 57. A powerful motorcycle can accelerate from rest to 26.8 meters per second. That's 100 kilometers per hour, which, by the way, that's 62 miles per hour or so, in only 3.90 seconds. A. What is its average acceleration? B. Assuming constant acceleration, how far does it travel in that time? Okay, so this sounds like a kinematics problem. So Vx initial, Vx final, these are the kinematic variables to write out. Delta x, t, and a. So there are the kinematics variables. The initial velocity, the final velocity, displacement, time, and acceleration. Okay? So it says it can accelerate from rest. So I think from rest sounds like 0 meters per second for the initial velocity. Its final velocity is 26.8 meters per second. And the time is 3.9 seconds. 3.90 seconds. We want to know what is the average acceleration. So this question mark right here is part A, the average acceleration. And then part B, it says how far does it travel in that time. So notice for part A, we're going to ignore the displacement. Notice ignoring the displacement is ignoring delta x. So we take the equation that ignores displacement. And that, I think, should be the definition of acceleration. So that's going to be the Vx final equals Vx initial plus Ax times t. Now, if we rearrange this equation for A, we can reconstruct the definition of acceleration. So we have to subtract Vx initial to the other side, and then I think we need to divide by time, and that should look familiar from earlier, because this is the equation for the definition of acceleration. And I think we can just put all the numbers in because we have all the values. So we can do 26.8 meters per second minus 0 meters per second, and we divide that by the time of 3.90 seconds. So we've got 26.8 minus 0, which is just 26.8, and divide that by 3.90, or just 3.9, the calculator doesn't care. And let's go 3 significant digits. Let's go about 6.87 meters per second squared, because each of these had 3 significant digits. So there's the acceleration. By the way, depending upon how large the acceleration is in these vehicles, like a motorcycle or whatever, that determines things like horsepower. We'll get to power much later this semester, but just keep that in the back of your mind. And then lastly, part B, we want to know how far did it go? Which equation can you use? Any one you want, man, as long as it's not the definition of acceleration, because that does not have displacement in it. So why don't I just choose the displacement curve? And I'm feeling lazy, so I'm just going to copy this displacement curve from the earlier problem. So here's the earlier problem. I'm just going to copy the displacement curve over. So there it is. And I think we have all the values. We can just put all the values in. So we can say delta x is v, and by the way, this Vx initial t, since Vx initial was 0, we can just make this term 0, which is great. So all we need is 1/2 ax t squared, so we just need 1/2 times 6.87, which we just solved for, meters per second squared, times the time of 3.90 seconds. And square it. So let's get that value. So 0.5, same thing as a half, times 6.87 times 3.90 squared. Calculator doesn't care about the ending 0. We've got about 52.2, or I said meters per second, but I meant meters. 52.2 meters is displacement, right? By the way, I suggest you put the units in here, because meters per second squared, this 1/2 is unitless. But look at this. Do you see how it's units of seconds squared? Do you see how the seconds are going to cancel? You just end up with meters, which is what we expect for the displacement.
So what we saw in these problems is that when you list out the 5 kinematic variables, it matters very much which of those variables you ignore. That variable will actually tell you which equation to choose. You'll have to have 3 pieces of information to be able to solve for the 4th, but the equation that you choose depends upon the ignored variable. And so if you don't have the initial velocity, you use that funny equation, which not a lot of people use, which is kind of like a modified version of the displacement curve. If you don't have the final velocity, you use that displacement curve, delta x equals v initial times t plus 1/2 a times t squared. If you don't have the displacement, use the definition of acceleration, v final equals v initial plus at. If you don't have the time, use the squares of velocity equation. And then if you don't have the acceleration, use the equation that takes into account that since there's constant acceleration throughout the motion, the average velocity is given by just the linear average of the initial plus the final velocity. So that's VO plus VF over 2, just times time. And then average velocity times time is the displacement. So hopefully that kind of makes sense. And it turns out you can solve all different kinds of kinematics problems with just these 5 equations and just this algorithm. And now that you understand the recipe, tell me, how are you going to use this in your real life? How are you going to use this in your classes? How is this going to help you? Are you going to tell your friends? Please let us know down in the comments. We always appreciate hearing from you and knowing what you would like to see in future videos. So thank you for watching the channel, and please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. Social media links are down in the description below. Please support us, and thank you for your attention. We will see you in the next video.